hyperbola.
Oh, that's what I was gonna say. A hyperbola. I love a good.
Hyperbola is
Yes.
actually the way you pronounce it,
Yeah.
but I mean, it's a fun one to mispronounce.
Hyperbola.
It's not a hyperbole either.
No, that's like
So-
one of them English things.
Yeah,
where
something like that.
You're on highlighter.
Yeah, I am.
All right.
Woo-hoo. Okay, so BT dubs on our note pack, our graphic organizer. It didn't print, so make sure you copy down what's going on here on this table.
And also BT dubs, this is super similar to the ellipses that we've been talking about.
Oh, absolutely.
Yeah.
The key difference is there's a minus sign instead of a plus sign.
Right. Now, order here is important, and we talked with ellipses that you could have, it didn't matter if you had X first or Y first, but since there's the minus sign now, it really is important.
It's so important. And here's what it changes. An X squared first is this graph that we've got on top here where your curve, which is the only part of this that's actually the hyperbola, is the curves on the sides.
Right.
We're just going to use, we're just going to use the rest of it to draw it. So if it's X squared first, it's on the left and the right side. If it's Y squared first, it's like this bottom graph where it's on the top and the bottom.
Right.
So it's super important.
So it kind of opens the direction of whatever's first is the easiest way to remember that.
Right, and notice that in both cases, A is the one that's first, B is the one that's second, and that's going to matter whenever we fill in our foci and our vertices, and then now we've got these new words. The transverse axis is the one that's between the vertices. So like on this top graph, the vertices are like, if you imagine that these kind of look like parabolas, the vertices are like the vertex of the parabola.
Like the vertex, yeah.
They don't actually behave exactly like a parabola, but they're U-shaped. So
Yeah.
so that's our vertices, and our foci are
They're actually going to be
in
the
here,
point,
right?
yes, the point that the graph curves around, just like with a parabola. So again, we've got this situation where the hyperbola is bent around a focus.
Yes. And this time what's going on is that each of these points ends up being a constant difference, whereas in
Right.
ellipse it was a constant sum, but
Right.
this is going to be a constant difference. And so the transverse axis is the axis that goes between the vertices. So this direction would be the transverse
Right.
axis. The conjugate axis, which would be the opposite one, would be the one that goes the other direction.
Now, here's an interesting thing that you need to remember with a hyperbola is that with an ellipse, we knew that our major axis was always the longer, the bigger number.
And that's not necessarily
that's not
true here.
necessarily true.
Because here, our transverse axis would be this one, and I believe that's the shorter
Looks
axis
shorter,
here.
right.
Because it's only 4,
Right.
and this one is 6. So, and then we do have asymptotes. That's what this x is asymptotes, and we can find the equations for those asymptotes. Our Pythagorean relation that helps us find C is the normal Pythagorean theorem for hyperbolas.
That's how it works for this
So
guy.
make sure you're paying attention because it's not on ellipses, but it is on hyperbolas.
Right.
You want to do an example?
Yeah, sure. You know, one cool thing about hyperbolas is, everything kind of bounces back towards that focus, I believe. Isn't that correct with the hyperbola?
You're talking about in like real world stuff?
Yeah, in real world stuff.
Well, I know it does that for a parabola.
Yeah, I think it
so
does too for a hyperbola.
I guess we'll have to find out.
Well, if you've got the old Dish Network satellite, this is some of the theory that allows the Dish Network. It's the hyperbolas and ellipses.
And parabolas.
I'm sorry, hyperbolas and parabolas, which allow those TV
It
signals
helps
to
them figure
receive.
out where to put the
The
receiver
inside,
to work
the
it best.
little-
It's actually at the focus of
Yeah,
the
the
parabola.
antenna point, right, the little thing that sticks up. Well, you can really have a lot of fun with your friends that have Dish by taking tinfoil and putting shiny side out around the
And the antenna
around
thing?
the antenna thing
Because
because
then it just reflects
then
back
it
and forth.
reflects it back into space.
That sounds like a terrible prank to pull on
Yeah.
somebody. Don't
So-
do this at home, kids.
And if you do, don't say where you got it from.
Example 1. Let's find the vertices and the vertices and the foci of the hyperbola. 4x squared minus 9y squared equals 36.
So we got to make it equal 1.
Yes, we do, because that's standard form. So I should divide everything by 36 in order to make that happen.
That's correct.
So that gives me x squared over 9 minus y squared over 4
Right.
equals 1. So the vertices, man, we don't have a chart in front of us. You want to go get like your book or something?
Yeah, I got it. I got it right here.
I will say that underneath the first thing, is a squared, so that means a is
We're going to
3.
actually start at 0. We're going to start at 0, 0. That's the center.
Right, the center of our hyperbola is at 0, 0 because there's no parentheses for x and y.
And a is going to be the square root of 9.
And b is the square root of 4, which is 2. And so our vertices...
You're going to move left or right.
Yeah.
So we're going to move left 3 and right 3 from the center to get our vertices.
So that should be plus or minus 3, comma 0.
Yep. That's it.
If x is first?
No, that's right.
Yeah, okay. Not like I'm doubting you or anything. So our foci...
Well, I feel like you are, but that's okay.
Okay. Our foci, we need to figure out what c is.
So a squared plus b squared.
Yeah, a squared plus
So
b.
square root of 13. Your writing today is terrible. What's going on?
I don't know. So that's 9 plus 4,
13.
Which is 13. And so we square root.
You may
So
just need to give up while you're ahead.
C is the square root of 13.
And remember, it's actually technically plus or minus the square root of 13.
And that ends up coming into
And that's where that
effect
shows
in
up,
our
right.
formula. So there's our vertices and our foci.
Right.
All right, next, find an equation of the hyperbola with foci 0, negative 3, and 0, positive 3, whose conjugate axis has length 4.
That's b. That's going to be the b part, half of that.
So half of this is equal to b. So b is 2. Sketch the hyperbola and its asymptotes to support your sketch with a grapher. Now, they're going to give us all kinds of different information like they did with parabolas and ellipses where you got to sit and sift through and figure out what is actually happening. Right. So for one thing, since it's a plus or minus situation, we know the center of this hyperbola is at 0, 0.
Right, because you're going the exact same distance both directions.
Right, and since the y changes, that is a situation where y squared is first.
Right.
We said that b is 2 because of the conjugate axis.
So that's got to go under the x. So that would be 4 under the x.
Okay.
2 squared.
Yeah, sorry, 2 squared, which is 4. And so now we're just stuck having to figure out what a is, but we know that c is
3, yeah.
Because
so
that's
c
a
is
part
3.
of the foci.
If b is 2, we can use our Pythagorean theorem then to figure out what a squared is. And remember, we don't have to square root this. So if we get some like really weird number like 17, we don't have to square root that. We just leave it as 17.
9 minus 4 is 5. What we want under here is a squared.
Yeah,
So we just put
there you go.
5 in
Bam.
there. Now, I think hyperbolas are kind of fun to draw.
They are fun to draw.
They're kind of intricate in some ways. Here, let's do this. All right, so it's centered at 0, 0. And what we do is we go up and down, because underneath y, we're going to go up and down square root of 5. We're going to go left and right 2, and we're going to make a box.
Hold on one second. You do that, and I'm going to do this real quick.
Okay, so up and down, I guess a little bit more than 2. Let me switch colors. Left and right 2. Well, that's not a perfect box by any means, but you know, things happen. All right, so once you have your box drawn, then it's time to draw your asymptotes. So they make an X through the center and through the corners.
Sorry about that. I had to handle that situation right away.
All right, and then you look at what's first here. Y squared is first, so our
we're
graph
going
is
up
at
and
the
down.
top and the bottom.
Right.
And it looks like U-shaped graphs. They
Right.
go towards the asymptotes, but they don't cross them because that's what asymptotes are.
Right. They're like little boundaries.
Yeah, so that's our hyperbola.
There
and
you
then
go.
if we were supporting with our grapher, we would need to, if we have an 83 or 84, you'd have to add x squared over 4 to the right side. You'd have to multiply by 5 and then
take
end
the
up square rooting.
And don't forget, you're going to do plus or minus on that.
Right. So
And it graphs it a little bit strangely when you do this too, by the way. But if you've got the Inspire, if you've got the latest version of the operating system,
which is key.
which is key as we've discovered today,
Yes.
then you can just graph your hyperbola right away, which is also really nice.
Yes. So this is what you should get if you solve this for y, and then you would put that into 2 different y equals, and it should give you something. And sometimes they can look kind of funny. It sometimes will actually show either one or both asymptote.
Right.
Because of the way the calculator works.
Right.
So,
All right, good talk.
example 3. Now let's talk about some that have a center not at 0, 0, but at some point h, comma, k.
And all the same things that we've done with parabolas and ellipses apply here. So just pay attention to your chart and make sure you know which direction you're opening.
Yes.
That's crucial.
So find the standard form of the equation for the hyperbola whose transverse axis it has endpoints -2, 1 and 8, -1, and whose conjugate axis has length 8.
So conjugate axis is the A.
No, it's the B.
Oh, sorry, it's B.
So you divide it
by
in
2,
half,
and that gives us B.
So that's 4.
Right.
Okay, so that's what B is.
That's B. Now
our transverse axis, the endpoints of it are the vertices.
Right.
Okay. Axis, it's the one that's between the vertices. So these are actually our two.
I feel like
something's wrong
that should be -2, -1.
Okay, this should be a negative.
Yeah.
So -2, -1. Our bad.
Yeah, we got to work with that. Otherwise, we're going to have a really weird shaped hyperbola.
We don't want to deal with. Okay, so notice the y is what didn't change, and so on our...
So if y doesn't change, but x does, so y doesn't change, x does, I feel like we're going left and right.
We are?
X first.
Yeah, so it's this situation right here, basically. The y didn't change. So in one of these cases, like -2 perhaps, would be h plus a, and then 8 could be h minus a. And maybe I did those backwards, but it should all work out.
It should work out.
It should work out either way, so that it doesn't.
Or to get to the middle, you could just do stop minus start to get your distance and divide by 2.
So -2 minus 8, which is -10, divided by 2, and that's 5.
That's 5.
And then you have to add that to the -2.
Right, which would be 3. So there's 2 ways to go about it, but either way, looky there.
So h equals 3.
Which is what we just said.
And then you would plug that back in and get that a is -5. But it's really +5.
Well, because you're going to square it.
You're going to square it anyway.
You're going to square it, it makes it 25.
So it could be either one. And so that's what we want to do is we said x was first. We just figured out what h was. And we figured out what a is.
Minus. And then the y coordinate never changed, so it's going to be +1.
That's right.
And we already knew b, so
is
bam.
4, so that's 16 equals 1. So it all depends on what they give us and figuring things out.
That was a bad box.
Yes. Example 4, find the center vertices and the foci of the hyperbola.
I know, I already can do all of that.
Yeah, you can. Absolutely. I believe in you. Let's start with the center. HK.
Opposite of +2, -2. Opposite of -5, +5.
And make sure that you're paying attention to the order. If these were flopped around, you'd have to make sure you
X
put
goes
y
with
with
X,
y.
yeah.
And X with X.
Rule number 1. Don't forget rule
Yeah.
number 1.
Yeah.
Okay.
So to find the vertices, we need to know what A is, and since this is 9, that means A is the square root of 9, which is 3.
Right.
So
X first, which means we're going to add and subtract 3 from both sides.
Right.
No, yes, right.
No, you turned the page.
Oh, sorry, you were looking there.
So we add to the X
that. I don't know why you're double checking me today.
I'm double checking you because when I don't, bad things happen.
I'm pretty much dominating these today, just saying.
Okay, so -2 plus 3 is 1, 5, and -2 minus 3 is -5,
Now,
5.
please go ahead and take the step that Mrs. Stevenson just took, because we can do -2 plus 3 and -2 minus 3.
We're super good at it.
If there's some sort of radical situation, then
You can leave that
that's
alone.
fine. But in this case, we know what we're doing.
We do. Okay, B is 7, and that's going to help us find C, because we need that for our foci. So 9 plus 49 equals C squared. That's 58 equals C squared.
Square root of 58. So
that's not...
I don't think that'll reduce, because what is that going to be?
That's 26.
26.
No, that's not 26. 29.
Yeah, 29. Yeah, it's no deal there. So now, please, you can leave the radical in there. There's no need to write out 2 long decimal.
And I put it on
So,
X, right?
Yeah, put it with X, because that's where the foci and vertices always go together.
Yes.
Always. And it doesn't matter which conic section you're dealing with.
Yeah.
Yeah.
Good word.
What do you got? What do you got in mind there? Comets.
Yeah.
All right.
So we have some more eccentricity, like we did with ellipses, but now it's a hyperbola, so it's a slightly different formula.
I like eccentricity.
I do too, and it still has something to do with how eccentric our curve is, how wide or whatever. But it's not quite as obvious. I feel like ellipses, it's like, oh, well, if on one end you have a circle, the other end you're going to have a really
an oval. Yeah, an oval as they teach the little children.
But in this case, I don't actually know what's going on with it. So,
I guess maybe it's talking about, wideness and narrowness still.
Yes, but these will be values bigger than 1 if it's
Of course they will.
Hyperbola.
Yes, of course they will.
Now we've got this problem here.
All right,
it's quite a problem. It's talking about a comet following a hyperbolic path. Did you know that comets follow a hyperbolic path?
You started talking about hyperbolic, and I started playing 2048. Sorry.
That's helpful.
Sorry.
So a comet actually follows a hyperbolic path. If you can imagine, basically, here's my xy axis and here's my center point for my hyperbola. And so over here, if our hyperbola looks like this U-shaped curve, okay, well, whatever it's going around, I'm going to pick orange, whatever it's going around, that foci, that's like our sun. Like here's our sun, which is the focus of this hyperbola.
Right.
The comet follows this hyperbolic path. So
right.
That's kind of neat. So that's what's happening in here. Now remember perihelion.
Now this is for a one-time only sort of comet, I would think. Otherwise it'd be more elliptical, correct?
I don't really know how that works. Maybe it does a hyperbola until it gets close to another sun and then does a hyperbola around that.
Isn't that an ellipse then?
Not necessarily.
I mean, I don't know.
Because then what if it goes this way and then it just turns around?
Just like puts on the brakes and changes directions?
Yeah. No, gravity. It doesn't have brakes. We're not comet experts. Okay, so so it has a perihelion distance, which last time we defined as the distance closest to
zero. Closest to zero.
No.
Closest to the focal point, sorry.
Yeah, so
it's
in
the
our
point
picture
on
here,
the hyperbola closest to the sun.
Right. We've got 90 here. And so let's think about what our different letters mean. For example, if this would be a vertices, and so the line in between there, right here, that's A.
Right.
Because we take our center and add
from
A.
the center to the vertex, yes.
And then to get to our focus, we take from the center to the focus, and that's C.
Right.
Okay.
And there's a couple different ways to recognize this.
Right.
One of the ways is we could say that A plus 90 is C.
Right.
Or we could say that C minus A is 90, depending on what we need.
Right. That's basically what we're getting from this first sentence. Then it tells us that when the line from the comet to the sun is perpendicular to the focal axis of the orbit, the comet is 281.25 gigameters from the sun. Now that line is perpendicular to the focal or not to the focal axis.
Yeah, to the focal axis, yeah.
Oh, the focal axis is this way, and so perpendicular gives us this, so
right.
That's 281.25. Okay, and so we're just going to have to tell you basically something that's true, that basically our focal width for a hyperbola is 74.
Sorry, yeah.
Our focal width is 2b squared over a. Okay, that's what our focal width equals. I think we're going to get there from this. So 281.25, that's half of our focal width. So to get our whole focal width, we need 2 times that.
Right, which only makes sense because we're going down the same distance that we went up.
Right, so what's 281.25 times 2?
17.
Not so much.
I'll punch it in. Whoops, that's the camera ones.
562.5.
Wow, how did you do that?
Oh, magic. So that means that we have 562.5 equals this focal width, which is 2b squared over a.
562.5.
Okay, thanks.
Okay.
So we can multiply both sides by a, perhaps, to get a slightly nicer looking formula. Okay, so that means...
That's a really big 2.
So that means that now we've got a system of equations that we can solve for a and b.
Dogs.
So, which of these is a better situation? Neither of them.
I
Secret
think
option number 3, a equals c minus 90. No, wait, because then we've got b. That's still not helpful. But we know that b equals what with our Pythagorean relation?
I don't know. What does B equal with our?
C
Do we know
squared
C?
minus A squared?
Oh yeah.
All right, so
No, plus for the hyperbola, isn't it?
it's
plus?
A squared plus B
okay.
squared
No, I
equals-
got you. All right, right.
it's
right,
A squared plus B squared equals C squared. So if I solve that for B, I would subtract C
Yeah,
squared.
gotcha.
So 562.5A equals 2 times square root of B minus A squared. Hey, that's convenient that we're squaring that. That gets rid of that square root.
Oh, thank heavens! I thought you were gonna have me punch in something on my phone again. You know, my iPhone doesn't have a square root thingy on it. See?
You got to turn it. Flip. No, just a 90-degree turn. There you go.
Son of a gun! Look at all that.
Look at all that stuff.
Whoa.
All right, now
What's an E?
now we can take A and plug it in here. Do you agree?
I agree.
Or should we take C?
Doesn't
Because
matter.
then
We're gonna
there's
have
less
to
plug
square.
in.
We're gonna have to square something at some point. So
Let's do C.
okay.
So C equals 90 plus A.
90 plus A.
Which we had earlier written down. So we can work that out. We
Yep.
can plug that into our calculator.
We can do all kinds of great stuff here. But one thing that you can do is go ahead and get rid of that too. So we're back to 281.25 equals 200.25a equals, and then if you square that guy, that shouldn't be hard to square out. Okay, 8,100. Okay, plus 180a plus a squared minus a squared.
So the A
so
and
the
A squared and
the
the
a
A-
squareds are gone. So look.
That's actually really convenient. So
it-
now we can subtract
Right,
180A
like we thought
over
it was going to be
and then
horrible,
divide.
and it wasn't. So 281.25 minus 180 is 101.25.
And then we're going to divide that over to the 8100. And that'll be A.
8100. Whoops. 8100 divided by 280.
101.25.
80.
Hey, wow, that's really nice. So A is 80. Now we're just going to do a chain reaction here probably to find our other things. Like we can know that C is 90 plus 80. So that means that C is 170.
Right.
And then once we know A and C, we can plug that in here and get B.
Right. Well, once we know A and C, we can find eccentricity.
Well, we're going to have to do both.
Oh, okay.
Right? So C squared minus A squared, do 170 squared minus 80 squared, and then square root it. Hey, you.
Boy, I don't have that kind of calculator. What'd you say?
C squared, 170 squared minus 80 squared. Yeah, this is hopeless.
Okay, hold on.
No, minus 6,400.
Hold on. Hold on. The Inspire to the rescue. What is it? 80 squared? It's 170 squared. Minus 80 squared equals square rooted 150.
Okay, so ABC.
How did you get that already?
And now E. So C over A. So 170 over 80, which you can get rid of the zeros, and that's 17 over 8, which as a decimal.
17 over 8 as decimal. I learned how to do this on my calculator. 2.125.
All right, so we've got A, B, C, and E. Now, what are the coordinates of the center of the sun if we coordinatize space so that the hyperbola is given by this standard form with the center of our hyperbola
Right.
0, 0?
Do we have to run this
So-
past NASA if we coordinatize space?
I don't think so. I think it's okay to coordinatize space in general.
Can you even say that word?
Apparently not. So the sun is the focus. So
Which is C units from our
and
center.
the way we have it set up, it's positive C
Right,
units.
right.
And so our C is 170, so it'd be at 0, 170.
Right.
Ta-da!
There you go.
Okay, so this problem, it's in the book on page 662, and they have a nice picture so that if you wanted to look at that, I'm going to attempt to draw a nice picture,
Yeah.
but theirs is like all,
When you have a professional
Cart-
artist, sometimes it makes
yeah, it's
it helps.
cartoony and whimsical, and it's great. So The idea is that with radio signals and light and all these different things that are waves, you can use hyperbolas, parabolas, and even ellipses have their kind of thing that goes with that. You can use those to model that behavior. So in
The
this
waves
case,
of
the waves of your
the
signal.
light or signal.
Right.
Okay.
And so with radio signals, that's what we're dealing with in this problem. We've got 3 different transmitters, and they're located at 0, Q, and R. And what's going to end up happening here, if we look at it nicely enough, 0 is at the origin.
Hey, wow, that makes things bearable.
Okay. O is at the origin, not 0. O is at the origin. R is 100 miles due north, so R is up here.
Oh, it's on an axis.
And that distance there is 100. Q is 80 miles east, so here's Q, and this distance would be 80 miles.
Okay. I see a right triangle in there. We may need it.
So the LORAN, which stands for Long Range Navigation, that receiver there's a boat out here somewhere. It's not a good boat color. Let me pick a good.
LORAN, I believe, is a sonar system stretched out across the ocean that allows boats and water traffic to help with navigation.
Oh, okay. It's kind of a big deal. So the sloop, that's a word for a boat, I guess.
Yeah, it's a
Gloria
sloop.
is out here, and it's got like receivers and stuff and transmitters so that they can all communicate. And it tells us that the sloop Gloria receives the signal from O, 323.27, that's microseconds.
Wow, that's really short.
Okay, after the signal from R. So it receives this signal 323.27 microseconds after it gets the signal from R, and then it tells us how long between the signal from O to Q. It asks us what's the sloop's bearing and distance from O. And so that's why this is neat, is because if we call this pinging, kind of. Like if you're pinging back and forth between boats and transmitters, then as long as you have enough points, you can have GPS coordinates for anything
It's
you
like
want.
on the submarine movies when you hear that really cool audio noise.
Boing,
Yeah.
boing, boing. That noise?
The
flashing thing. You know what I'm talking about? That's what you were talking about, right?
Totally what I was talking about. But the whole head movement with that was what intrigued me. Okay.
Thanks. Okay.
It could be some special edits later.
One thing that we do need to know is that there are 980 feet per microseconds. That's a mu right there, by the way, in case you're like, what is that?
Greek letter.
Yeah, okay. So that is how fast radio signals travel.
Which is pretty quick.
Yeah. That must be something similar to maybe the speed of sound. Maybe that's the speed of sound, because radio waves. No, radio waves aren't
I don't think
really
they can
sound.
travel as fast as light.
But anyway.
Yeah. Here we go.
Anyway, so what we're basically doing is we're gonna put a hyperbola here. Okay, we've got this hyperbola, and I realize those aren't perfectly symmetrical. We've got one hyperbola facing this way, and that's the path the radio signal takes to get to Gloria. And then we've got another radio signal going this way.
How do they figure all this out?
I'm going to guess that they guessed and got it right, and then we're like, oh, look at this
Hey, let's
math.
make a problem.
All right, so what we're trying to do is find the 2 equations for these 2 hyperbolas, and then if we can graph them and find the point of intersection, that's where Gloria is.
Okay.
So, step number 1.
So when the radio wave comes off, then it goes out in that shape.
Yes.
Okay.
So the OR hyperbola that we have, O and R are the foci of that hyperbola.
Right.
And it would have a center halfway, right?
Right. So 50.
Yeah,
0,
at 0, 50. So that's going to be helpful because it's a hyperbola up and down. So we've got y squared would be first.
Right. And then the x, just x squared. Yeah.
Right,
So it'll be y
so-
squared minus 50. We just need to figure out what needs to go underneath on the bottom.
And so to do that, to find A, which is this distance right here, we're going to use the microseconds they gave us times the radio signal speed and then change it from feet to miles. Okay, so
Because we have feet per second.
right, we have right now 323.27 microseconds, but we want this to be a distance. So you times it by this.
Because we
This
need to
is
know,
dimensional
we need the actual
analysis.
distance part from the center to a point on the curve.
Right.
And when they gave it to us as a rate of change, then by doing some dimensional analysis, we can eliminate one of those things and get it to where we just have the distance only.
Right,
So use what we know to find what we don't.
right.
Okay.
So if we work this out like on our calculator, surprisingly enough, we end up with 60 miles, which is just a lovely, that's a lovely,
Well, that's nice. 60's,
really nice.
60's round.
and that actually gives us 2a. That's the length of our axis.
From the whole axis. So
Yeah.
from the vertex of each part of that hyperbola, the one bending around O and the one bending around A, the distance of that major axis is 60.
Right, so that means a would be 30. And
From the 100, or from the 50, right? So you're going to go up 30 and down 30
yes, from 50.
to get your different vertices.
Yes,
Right.
so a is 30, which means we put 30 underneath y.
Squared.
30 squared underneath y. And then we need to figure out what b is, but we can do that because we know that the focus here,
We know where that is.
we know, yeah, because this is a length of 100 to get to this focus. So between these is 100. So how far is it from 50? It'd be the center point.
50.
So it'd be 50. So that's C, right?
Yeah.
So we got to do the Pythagorean theorem on
Right.
that.
So we
because
know what
that's
C
our-
is. We know what A is. We just need to know what B is.
So 30 squared plus b squared equals 50 squared. So 50 squared minus 30 squared, and square root that is 40. Oh, well, that's a bad way of writing that. B equals 40. So we put 40
B
squared
equals
on the bottom
basically
of this.
2,500 minus 900,
Yes.
which is 1,600. The square root of that is 40.
Okay, and
All right.
so this is our equation, and we can rewrite this with these squared, but we're gonna put it in the calculator anyway,
Right,
so we can
so
do
that's
that
okay.
later. Let's do the other hyperbola. So for our hyperbola that's OQ, that has x first, and our center, if that's 80 all the way across, is at
Center
40
would be
comma
40.
0.
And that would be with the x coordinate, not the y coordinate this time.
So x minus 40 squared, and then we don't need the parentheses there, we just need y
You
squared.
did the same thing.
I
just a
know,
second ago.
right? What's wrong with
I
me?
don't know.
So then to find the 2a part here, we do,
We look at the second rate of change they give us, and we perform dimensional analysis again to get just a distance and lose the rate of change. So, lucky for us, they gave us that key bit of info about how many feet per microsecond.
yes, couldn't do it without that. So if we work that out, then we get 48 miles.
Wow, that's really convenient.
Yeah, it is. Somebody did a good job writing this problem. So
guess
a
so.
equals 24. Actually, that might
half
be
of that-
rounded because it has a little approximate symbol on
Okay,
it.
that's okay.
A is 24, so on the bottom of this
24
would be
squared.
24 squared. And C in this case is, since it's 80 all the way to our foci,
Right,
and our center is at 40, so that C would be 40.
right. C is 40. Just
Okay.
like in the previous problem, the 50, which we already knew.
And so we do A squared plus B squared.
Jeez, Mr. Aldstein.
C. So 40 squared minus 24 squared, square rooted is 32. So B is 32, which gives us 32 squared on the bottom of this.
That 2 has a long neck. Okay, so the math so far hasn't been that bad. The dimensional
Knowing what
analysis
to
is
do
yeah,
is the
knowing how to
issue.
get started would be the most difficult part.
Right.
But now we've got these 2 equations. What can we do next?
We can graph them. We can, if you have an Inspire, you're lucky because you can just plug them in as is. If you have an 84, you're going to have to solve these for y. So I'll start with the first equation, solving for y. I'll just make that 900. So you'd add the x squared over 1600 to the right side. You'd multiply by 900, then square root, then add 50. So y minus 5 squared equals 900 times x squared over 1600 plus 1. And then square root both sides, so y minus 5 equals plus or minus the square root of 900 x squared divided by 1600 plus 1. And then add 5 over. So y equals 5 plus or minus the square root of 900 x squared over 1600 plus 1. So you'd have to put that in, you can put the plus and the minus, but really we just are concerned with the top one, which I'm guessing would be the positive, but I don't know. So you could test it out. You could type it in once.
Oh, I was typing. Sorry, while you were explaining, I was typing on an Inspire.
So you could see if it graphs the right one. We really just need the top one and the right one of these. So the other one, if you just kind of follow, actually it's going to be almost completely different since we're trying to get y squared by itself. We'd have to add y squared over, which means we'd have to subtract 1, so that we've got x minus 40 squared. I don't know what 24 squared is off the top of my head.
24 squared is 24 squared.
324. No,
I don't know.
That's not right.
That can't be. I don't feel like that's correct, but you may be right.
No, it's not. I also don't know what 32 squared is off the top of my head, so I'm just going to leave them be. So you'd multiply by 32 squared?
We're wanting first quadrant, correct?
Yes.
Okay.
So you multiply by 30.
Ooh, these are really big.
I did not. That one's supposed to be on the other side.
We go to we're going up to 100 on x, right?
Subtracting 1 over. Okay.
So let's go up to.
So now I would multiply by 32 squared on both sides and then square root. So
I found a point of intersection.
and so once you have it graphed and they should intersect, then you can find the point of intersection using your calculator, the tools you have there. Y equals plus or minus 32 squared times x minus 4 squared divided by 24 squared minus 1. Good thing we just have to put that in the calculator and not actually figure
I got
out.
I got 187 and 193. 187.085 and 193.485.
Well, that sounds reasonable to me. Does it sound reasonable to you?
Yeah, and hey, it matches the book.
Okay, so to find the bearing and direction for this.
The bearing and direction?
The bearing you use, this is taking it back a ways, you use inverse tangent of y over x.
Because we've got to get the angle of measure from 0, so we got to actually work from what we know already with our trig stuff, okay? So this is going to give us the angle off of the x-axis.
And once we have that angle, we have to do 90 minus that.
Right.
Because the bearing starts from up here. Our calculator's going to give us this angle.
Right.
We want the bearing, which is this angle,
right.
from north. And so if you do that, 90 minus inverse tangent of that fraction.
Right. And so carry that through. Try to keep your answer in there. Try not to round if possible.
Right. You should get 44.04 degrees. That's our bearing. The distance from 0 to Q, you would just, that's a right. Hey, you mentioned a right triangle.
Oh my
earlier.
gosh, I did, didn't I? Wow,
There's
there it
a right
is.
triangle
There's a
there
right triangle.
with sides 187 and 193. So we just do the Pythagorean Theorem on that. So
to get the hypotenuse.
187 squared plus 193 squared, square rooted, gives us 269.15, and we're in miles because we converted earlier to get into miles.
Wow, that's a lot.
That's quite a problem.
That's a problem.
That's whew.
But there you go. There's not getting lost on the ocean right there.
Yes.